Okay, some solved problems for Chapter 16. We're looking for a force between two positive charges. I've gone ahead and drawn the picture out. One thing to kind of be careful of is here we have a micro Coulomb, so times 10 to the minus 6 coulombs. Here we have a millicoulomb times 10 to the minus 3 coulombs. Both of these charges are positive, so I expect the force to be repulsive, but it's only asking me for the magnitude, so I don't really need to know that. Again, convert 16 centimeters to meters. So we write Coulomb's law. Force is equal to K times Q1, Q2, divided by the distance of separation squared. The most common thing I see, don't forget to square that guy. And K is simply going to be 9 times 10 to the 9th. Charge number 1, 25 times 10 to the negative 6. Charge number 2, 2.5 times 10 to the minus 3. 0.16. Again, don't forget to square that guy. And I'm going to come out with the force to be about 2.194 times 10 to the 4th newtons. And just a little more practice using Coulomb's law. We have two small spheres, and I'll draw my two small spheres. I know how far apart they are initially. That's going to be 6.52 centimeters. And then these two spheres are moved, and the force is going to have tripled. So we know that these two spheres are going to be much closer. And so we're going to say, go ahead, I got R1 and I'm looking for R2. One thing I also know is I have Coulomb's law here, but I also know that force 3 is going to be 3 times force 1, the force tripled. So force 1 written as such, force 3 written as such, and essentially what I'm going to do is I'm going to say, well, 3F1, 3 times F1, that must be equal to force 3. So now I'm going to say, hey, I'm going to set this guy right here equal to that guy right there. Now, a lot of things are constant here. K is going to be a constant. Q1 is going to be a constant. Q2 is going to be a constant. And what I'm left with is 3 over R1 squared is going to be equal to 1 divided by R3 squared. Go ahead and solve this guy and say R3 is going to be equal to the square root of R1 squared divided by 3, or R1 divided by the square root of 3. So R1 is going to be 6.52 centimeters. Divide that guy by the square root of 3, and we're going to get 3.76 centimeters. And now some Coulomb's law in 2 dimensions. So we have some charges that are kind of lined up on a triangle here. It tells me that it's an equilateral triangle, which tells me that this angle right here is 60 degrees, same with that one, and the same with that one. And I'm looking for the magnitude of the direction of the force on each particle due to the other two. So I'll just kind of label these guys 1, 2, and 3 so I can keep them straight. Now we know that these charges are all positive, and so the force is going to be repulsive. And let's just take a look at particle number 1 here for a second. It's going to feel a repulsive force due to 2 in that direction right there, and we know that this angle is also going to be 60 degrees. Look at 1 and 3, they're both positive, so it's going to be a repulsive force in that direction. Force on 1 due to 3. Now the force, we can write that using Coulomb's law, KQQ over R squared. All these charges are equal, so we can kind of simplify this as such. Now I've gone ahead and written force 1, 2 and force 1, 3 over here to save me some time, but I need to worry about direction here. So I need to break these guys into their components. So here I'm going to say this is going to be force 1, 3 in the x direction, and then right there, that's going to be force 1, 3 in the y direction. Take a look at that angle right there, that's 60 degrees. That tells me that force 1, 3x is going to go like the cosine of 60 degrees. Force 1, 3 in the y is going to be force 1, 3 multiplied by the sine of 60 degrees. And I've just gone ahead and written all this. See if you from watching me scratch all that out. One thing that you have to pay attention to is the direction. Here I've said that force 1, 3 is going to be in the negative y direction, or force 1, 3x is going to be the negative x direction. This one is going to be explicitly positive, and both of these guys are going to be in the positive y direction. So, do the sum of the forces in the x direction. These two are going to cancel each other out. So we know that the force in the x direction, the net force, is going to be equal to 0. Add these two guys together. Tells me that the force in the y direction is simply going to be 2 kq squared divided by r squared sine of 60 degrees. Now it's a simple matter of saying that the net force in the net force is simply going to be the force in the y direction. So I've gone ahead and said there's no force in that direction. So 2 times 9 times 10 to the 9th times the charge, 17 times 10 to the negative 6. Don't forget to square that guy. Divide that guy by the distance, 0.15. Again, square that. Sine of 60 degrees. You type all that into your calculator, and you're going to get 199.96 newtons. And now we have an electron that's going to be in an electric field. So I've kind of drawn it. Drawn my electric field is pointing to the east, so west is kind of over here. And I'm just looking for the force on that. I know that force is going to be equal to the charge times the electric field. Charge is just that of an electron, which is going to be negative 1.6 times 10 to the negative 19th. So negative 1.6 times 10 to the negative 19th multiplied by my electric field, 2460 newtons per coulomb. See, the units are going to work out, and I'm going to get 3.94 times 10 to the negative 16th newtons. The direction, well, the negative sign means the opposite direction, so west. Direction, magnitude. And some practice calculating the electric field, again with 2 dimensions. So here I've got some, kind of got a square right here, and it says I've got some charges, and they're all going to be positive charges. And it's saying, hey, what is the electric field at this one corner over here from those other 3 charges? So positive charges, draw my positives on there. That says the electric field is always going to be pointing away from them. So I would kind of draw my electric field 3 in that direction. I draw my electric field 1 in that direction. And then my electric field number 2 would be kind of coming off in that direction. And I know that this angle here is going to be 45 degrees because it's a square. Now what I also need to do is I say, well, electric field is simply going to be kq divided by r squared. I'm going to say E3. Well, let's go ahead and calculate that guy out. So 9 times 10 to the 9th. Go ahead and say my charge is going to be 3.25 times 10 to the negative 6. And the distance is simply going to be 1.2. And again, don't forget to square that guy. And we're going to say E3 is going to be equal to 19,652 newtons per coulomb. And this is just going to be in the y direction. Kind of look at the symmetry here, and you can say, well, E1, I'm going to be typing in all those exact same numbers, 19,652 newtons per coulomb, and this is going to be in the x direction only. Now if I want to figure out what the electric field from 2 is, I need to know this distance right here. That distance is, using the Pythagorean theorem, simply going to be the square root of 1.2 squared plus 1.2 squared. That's going to be that distance. Go ahead and you type all that in. It's going to come out to be about 1.7 meters. So E2 is simply going to be equal to 9 times 10 to the 9th times the charge, 3.25 times 10 to the negative 6. Divide that guy now by 1.7 squared, and we're going to get 10156.25 newtons per coulomb. And what I want to do is I want to break that into the x and y components. Let me just explicitly write that this is going to be the x and the y. Kind of say that E2y is simply going to be E2 multiplied by cosine 45. E2x is going to be E2 multiplied by the sine of 45. Go ahead and you type all that into your calculator, and you're going to say this is going to be 7181 newtons per coulomb. And actually the same is true for this one, 7181 newtons per coulomb. And lastly, just going to say electric field in the x direction, that's going to be E2x plus E1x. E3 had no component in that direction, so you just add those two numbers together, and you're going to get 26833 newtons per coulomb. I'm going to do the same thing, say E in the y direction is going to be E2y plus E3y. E1 had no component in that direction, so 26833 newtons per Coulomb. And lastly, my net electric field is going to be the square root of Ex squared plus Ey squared, Pythagorean theorem. Go ahead and you type all those in, and you're going to say that the net electric field is going to be 37948 newtons per Coulomb, so that's the magnitude. And symmetry would give you the direction, or you could say that the theta, or symmetry would say that this is not going to be 40. Symmetry would say this is going to be a 45 degrees, or you can go ahead and calculate that out. Okay, some more practice using the electric field. So we got 2 point charges, and we're looking for this point right here where the electric field is equal to 0. You can kind of see that. We'll just say that both of these are positive charges for a second here. Say that this is going to be the electric field from 1. It's going to be the electric field from 2. And we're going to cancel them out. Or these two are going to cancel out, so we'd say electric field 1 must be equal to electric field 2, just in opposite directions. So electric field is going to be kq1 divided by the distance squared. So here's just, the distance is just L over 3. Make sure I square this guy. And that's going to be equal to kq2 divided by the distance squared. If this is 1/3, and this distance right here has got to be 2/3. This all got to add up to be L. So this is going to be 2L divided by 3. Make sure I square this guy. And you can kind of see, well, the K's are going to cancel out. The L's are going to cancel out. And since I'm looking for this ratio Q1 over Q2, it's just a little bit of algebra. I would essentially say it's going to be 9Q1 is going to be equal to 9Q2 divided by 4. So that tells me that Q1 divided by Q2 is simply going to be 1/4. And a little bit of practice using Gauss's law. So I've got some box, and it's kind of enclosing some charge, so I got some charge in there. And it tells me that I know that the total electric flux coming out of this box is going to be this number right there, and it's asking, say, hey, what is the charge enclosed? Well, I know that the electric flux is going to be equal to the charge enclosed divided by the permeability of free space. So very simply, Q enclosed is simply going to be the flux, which I know, multiplied by the permeability of free space, which I know. So 1.85 times 10 to the third. So that's my flux. Permeability of free space, 8.85 times 10 to the negative 12th. And that gives me my charge enclosed is simply going to be 1.64 times 10 to the negative 8th coulombs.